Okay, so we'll get into clustering methods now, okay? Okay, and so clustering methods, this is what we call unsupervised learning. This is all right, so with clustering methods and unsupervised learning, here we don't have answers. We don't have answers or labels to our data, right? So in a classification problem, so versus when we had classification, you had X variables, and they all corresponded with some kind of label, right? You had some kind of label or a class. You had these data points. We had the answer, right? So we kind of have like given answers, and we train our model based on the data points where we have answers to them, right? So we train our model based on these given values. Okay. On the other hand, unsupervised learning, there's no answers. We don't even know what we're really looking for. I mean, we're hoping that there's structure in the data. Okay. So with unsupervised learning, principal components analysis is technically unsupervised learning because in that case, we're also searching for some kind of structure in the data, and we haven't given any kind of answers, right? So here, we seek structure in the data, okay? But we aren't given any quote. We aren't given any answers. Okay, and so, let me just kind of contrast. With a classification problem, you have something like, you've got data points over here of a certain label. And then you have other data points. And based on these things, you try to create a classification. Okay, with clustering methods, you have no labels. All the data points, they kind of just look the same. Now, when we look at this graph, our brain picks out two clusters, okay? Our brain is able to pick this out, but as far as the data goes, we don't have any kind of labels, okay? So no labels are given to the data. No labels are given. All the points effectively look the same. Right. And so, can we identify some structure here? And we've looked at principal components analysis where we're looking for a projection that maximizes the variance after we've projected the data, right? So that's one way to look for structure, is to maximize the variance. Okay. The method we're going to look at today is called K-means clustering. I'm missing a joke here, but okay. So don't mix this up with K-nearest neighbors. K-nearest neighbors is a classification method. Today, we are looking for K-means clustering. Okay, the algorithm is pretty straightforward. Okay, so I'll kind of describe how this works, and I'll describe the methods and I will leave it to you in a future task, probably the final, where you'd have to code this up. Okay, so so you can start to contemplate how to go about coding up the K-means clustering algorithm. Okay, and so basically the initial step is, well, okay. First, you start off. You have to pick your K. Okay. And this is a tricky thing, okay? But just, you pick a K. So let's say we pick K is equal to 2, okay? So for example, e.g. K equals 2, right? And then you just start up with some initial assignments. Okay? At this point, it doesn't matter. You just randomly assign some of your data points to class 1 or cluster 1, and some of the data points to cluster 2. Okay, so just, or I mean, you might have some better way, but you can do random assignment. Randomly assign data points to class 1 or class 2. All right, so let me just kind of show you what this might do. Let's say this is our data. I've got 6 points over here and 6 points over here. Okay, so I'm going to just randomly assign some of these. Okay, it doesn't really matter. So I'll put some. We'll just say this is red, and this is red, okay, and then these other ones will be blue, okay, doesn't matter. Okay, so then within these two, so once you figured this out, now you calculate the centroid of class 1 and the centroid, so we'll just say the centroid of class 1 and the centroid for class 2. Okay, the centroid basically is going to be, if here we have 2 dimensions, x1 and x2, basically you just do the sum of x1 divided by n, okay, for the points in class 1. Okay, so this is going to be your kind of x1 bar. And then, so you'll get a centroid will be a coordinate point x1 bar, x2 bar for class 1. And then you get the same thing over here. X1 bar and X2 bar for class 2. Okay. So, you know, I don't know what this is going to be, but effectively I'm going to get the centroid, and here I'm going to just pretend this is my centroid right here for the blue, and then I'm going to pretend that for red it's, I don't know, we'll say over here. Okay? Is that okay? I just made these up. I don't know. I'm real eyeballing, and maybe this is not a good eyeball location. But let's just say this is what we have, right? After your initial assignment, they're going to be pretty close to each other, these centroids, most likely, just from random assignment. But they're not going to be exactly the same. Okay? So here, I will pretend this is centroid class 2, centroid for red, and this will be centroid for blue. Is that okay? This idea of a centroid? All right, and then what we do next, so let me, whoops, that was the wrong tool. Okay. All right, and in this case, the K-means clustering is going to converge very quickly. But so here I've got my centroid for blue and my centroid for red, okay, right here and right here. And then what we do now is we go through each data point. So now that you have centroids, okay, reassign every data point to basically the class whose centroid is closer. All right. So basically, we just go through every data point, and so we look at this first one right here, and we say which one is closer, the red centroid or the blue centroid? And we go, well, that one, the red centroid is closer. Okay. And we go to this point. For this one, which one's closer, the red or the blue? We say red. This point, which one's closer, red or blue? Okay, red. Which one's closer, red or blue? And all of these, if we ask which one's closer, they're all going to be red, right? And then we come over here and we say which one's closer, blue or red, blue. Which one's closer, blue or red, blue. Which one's closer, blue or red. I think all of these very much clearly the blue one is closer. Okay. So we just assign every data point to the class whose centroid is closer. Closer will just be defined by Euclidean distance. I mean, you could use a different distance measure, but Euclidean distance is generally the most commonly used one that we have. Okay. And then after that, now you just iterate. Okay. Recalculate your centroids. Okay, and then so once we do that, so these are all now class red, and I would say, okay, well, what's the centroid of all of these data points? It's probably going to be like right here. These are all blue. Okay, what's the centroid of all of these data points? It's probably going to be right here. Okay, so we recalculate the centroids, and then we go again. We reassign all of our data points. Reassign the data points to the nearest centroid. And then you just continue iterations until all of your cluster assignments are stable. And that's it. That's K-means clustering. That's about as easy as it gets, right? I don't know. Should we code this up right now? I'm gonna have to think of a different assignment to give you guys for the final. No. I think I'll leave this for the final. I think it's like easy enough, but it's like also satisfying to to code this up and see it. Okay, and so I think what a fun, when you do the, I will probably have you guys after you recalculate the centroids and do this, create a plot, and you can kind of see the data points and the current assignments, and then you'll see the next iteration, and then you'll see a plot after every iteration, and it's kind of fun to see the centroids move towards the center of each cluster. Yeah.
How do you decide K other than just like looking at it?
Yeah, that's hard. Okay, so how do we decide K? That's there's no easy answer there. Okay, let me read about. So yeah, this is the part we have to pick K before we start doing the analysis, and then what happens when you pick too many Ks and all sorts of stuff. Yeah, I guess the answer is it's complicated, and then you just you go through and you kind of create your clusters. You pick a K, you test it out, you see what happens. You pick another K, and then you test it out and you see what happens. And then you kind of just look at the resulting things, and you get a little bit of a sense of, maybe this structure makes sense or maybe it doesn't. Yeah, unfortunately, we don't have very good the answer is not straightforward on picking K. That's the bottom line. Yeah.
For defining stable, do you mean if there aren't any new reassignments?
Right. If there's no more reassignments after you calculated your centroids, and then none of the new points get reassigned, so you can kind of compare the last iteration's assignments to this iteration's assignments, and if there's no changes, then you say, yeah, it's reached a stable convergence here. Okay. The Kmeans clustering, it fails when there is more information to the clustering than Euclidean distance. Okay, so right now, this is a simple thing, and all of the assignments get assigned based on whose centroid is closer. Okay, and that's defined by Euclidean distance. Okay, so this is. Okay, so let me write this. Okay, so K-means clustering works best in situations where Euclidean distance is kind of a good measure. Okay, in situations where is a good measure of, quote, similarity. Right. So, if you're dealing things with in real life, Euclidean distance oftentimes works out well. Okay, but if let's say you have a data set like this, okay, and then okay, now when we look at this, our brains, which have, I don't know, developed pretty good clustering algorithms without having to think about it, we would probably say, oh, okay, I see a cluster here, and then I see a cluster over here, right? This is probably what our natural tendency would be when we kind of look at this data. Okay, if we tried to apply k-means clustering here, though, what would end up happening is, let's say I initially start off with the answers, okay, right? And if I start off with the answers and k-means clustering works for this kind of data, then my assignments should be stable, right? If I've given it the answers, then my assignments should be stable if we're going to try this out, right? So if I start off with the answer, then my centroid for the red point would be right here, and my centroid for the blue points would be somewhere like right here, okay? What happens? Okay, if we look at this point right here, this one's going to get assigned to what? It's going to get assigned to the red cluster. Okay. If we look at this point, this will also get assigned to the red cluster. This point will also get assigned. This one looks pretty close. I don't know. Maybe just for illustration, we'll say we'll throw this one at the red cluster also. Okay. And then this one, yeah, this one's also closer to the red, I think. Okay. And then we're going to get these ones are closer to blue, right? And then, so what's going to happen here? Okay, we're going to get, so all of these get assigned to blue, and then so my blue centroid is going to move in this direction, and then my red centroid is going to get pulled also in kind of this direction after reassignment, right? And so we're going to get the boundary for k-means clustering is not going to work very well here, okay? So k-means clustering, it's a simple algorithm, and it works very well in situations where Euclidean distance is a good measure of similarity. Okay, but over here there's another aspect. It's not just the center, but over here we're going to say that the red data points don't differ very. We've got to include something where something to say the spread for the red data is a lot smaller than the spread for the blue data, right? For the blue data, we're okay if there's a large distance from the center. Whereas for the red data, we don't want that, okay? And so for data like this, we would need to incorporate something else, okay? So this is a situation where k-means clustering fails. We need to incorporate additional information. Other than Euclidean distance. Okay. So we might want to say something like, for red, we want to be close to the center. And the spread should be low. Okay, and then for blue, obviously, closer to the center is good, but it is okay if the spread is high. So on Friday, we'll take a look at the EM algorithm, which can allow for stuff like this. Okay. So this would be a better candidate for the EM algorithm. Okay. Well, okay, and then another illustration we could have data that looks like this. And then we'll have data that kind of surrounds it, like the solar system or something, I don't know, asteroid belt. This is, I don't know if this ever happens in real life, but this is the illustration we're looking at. Okay, obviously K-means clustering is not going to work well here either, okay? But we can do a kernelized version of K-means clustering. Okay, so, you know, regular old okay, one option is to perform kernelized K-means clustering. Okay, what does it mean to do kernelized K-means clustering? Okay. Kernelized here means we take our data and we project it into kind of like a higher dimensional space. Okay, so here we've got two-dimensional data, and then here we would project it into another higher dimensional space, and in the higher dimensional space, perhaps K-means clustering will now work. Okay, so we project our data into a, you know, kind of a higher dimensional space. So it's kind of, I don't know how I'm going to illustrate this. So, I mean, we can imagine this data being kind of projected into, so that, you know, when we look at the shadow of the data looks like this, but it could be such that, you know, this is like high up against the, and then we have like, the data is down here. Okay. This is kind of the idea here, and then we might be able to create, you know, a cluster down here where all of these get assigned to this one, and then and a cluster up here where all of these get assigned. I don't know. This is like the worst picture, but you know, a higher dimensional space that that allows us to do such a thing. Okay. Okay. And then so now, instead of Euclidean distance, we're going to have a kernelized distance. Okay, so instead of Euclidean distance to measure the difference, a kernelized distance, okay? Okay, and so let me. All right, I guess I'll write this out. Here, let me go on to the next slide here. Okay, so the kernelized distance okay, we will use d sub nk, okay? This is the kernel function at our point x, okay? This is the kernel function at x. Okay, so this is now the kernel function between kind of the points xn and xm, okay? Okay, and then now we're going to look across coordinates of pairs of points, zmk and zrk of the kernel function applied to okay, I know this is like a mess here. All right, so what's going on here is that we are taking kind of we're looking at pairs of points are m and k, m and r. Okay, we have and we're applying kind of this kernel projection trick to get this a distance, kind of a different distance measure. All right. Let me. I think this will be best illustrated if I can get you a code example. I haven't coded anything up here. I'm trying to think what I can do. Okay. I'll code something up here, and I'll show you how this the kernelized distance can kind of work for the funny-looking data sets here. Okay, we probably won't actually have to do some kind of messy operations here. So anyway, we'll wrap. We'll clean this up later. Okay. Okay. So anyway, K-means clustering. The initial algorithm using Euclidean distance. It's very simple. Works out very well. I think you guys can code that up very easily. Okay. Again, it fails when you need to include information other than Euclidean distance, okay? And so in this case, situation like this, the EM algorithm will be better, and we'll take a look at that. If not on Friday, then the following week. It's just a tiny bit more complex, but it's not too bad, okay? And then the kernelized K-means clustering can also work in situations where we want to we want to project the data into a different space, okay? But here I'm going to have to mess. I'll code up an example here that I think will be better than throwing this crazy math formula and function up on the screen here. So I'll do that, and then we'll take a look. And so this is we'll do clustering examples, and then we'll and I think that will cover pretty much a lot of what I want to take a look at from this from our textbook here. So regarding next week, I don't know if you guys have any topic requests. Maybe I can take a look at one or two topics that are of interest to you guys. If you have suggestions, I'll hear them out. I'll see what I can do, what I can put together in a few days here. If not, we'll figure that out as the time approaches. Okay, we'll see you then.